No sexista.
Good morning, everybody. Begin. Today I'm going to talk about structural decomposition analysis, and I'm going to do this in three parts. First, the basics, that's the easy part. Then I'm going into some integrated details about constant prices, this kind of things, extensions, and I will end, let's see how we're doing in time, with some applications. But the applications are, from a technical point of view, less interesting. For those of you who are at a certain stage experienced in structural decomposition analysis, there are similarities to other parts. So the basic idea is that we have a change in one variable that changes over time. We're going to split the change into, let's say, the approximate causes of that change. And there are clear similarities with growth accounting in economics, with shift share analysis that is a lot used in regional economics, regional science, and index decomposition analysis. And that application I've seen basically for energy and environmental type of structural decomposition analysis typically is used in an input-output framework because it can handle changes in matrices and vectors. So all this information is very interesting, but first we need to know how SDA works, and therefore I'm going to start with the most simple example in a minute, or simplest case. So we've seen this a couple of times before. We have the input-output table, just a national input-output table. Here the intermediate deliveries, a single vector to simplicity that all the final demand categories are aggregated into one. The outputs, we do have a full, in this example, in this case, a full matrix with imports, and we have a row vector with values added per instant. We calculate the matrix of domestic input coefficients. We do some input-output analysis. We structure the accounting equations. We arrive at the input-output model that we've seen on Tuesday. X equals AX plus F, and the solution is the Longchamp inverse times the final demand. And that is the starting point. So this is the simplest case that you can consider. We have one variable that consists of the multiplication of two other variables. So X equals LF, where L is, of course, the Longchamp inverse, it's the matrix, and F is the vector of final demands. We're going to look at the change over time in the final demands, in the outputs. And the question is, how much of this change can be attributed to changes in L and to changes in F. So we take two periods in time for simplicity, 1 and 0. So that means L1 F1 minus L0 F0. Now, I want to have some fun as well. And for me, the maximum amount of fun, it's hilarious. I'm roaring laughter in a minute. I'm going to add 0 here. So plus 0. Perhaps you have a different kind of humor and think this is not funny at all. Fine, but let me have my fun. At least we do agree that if I add 0 here, at least it's correct. So there's the 0. Now, a 0 in this case is, what is that? All right, L1 F0. And now I'm going to change the parentheses. So I'm going to change the parentheses here and here. Now, this gives me 1 times F1 minus F0. And this part gives me L1 minus L0 times F0. So there we have a decomposition. And the interpretation of this part, the red part, is what would have been the change in the outputs if only the Leontief inverse has changed as actually did. Anything else here, anything else is only the final demand, would have remained the same. And sometimes if you express this in this way, people say, well, it's that's change. That's a bit strange. Well, maybe that's a bit strange. On the other hand, this is what economists always do. They call this the ceteris paribus clause. So change one thing and leave the rest out. And the other term indicates how would the outputs have changed if only the final demands would have changed. And the rest, that is the Leontief inverse in this case, would have remained exactly the same. So that is the first decomposition. Now, yeah, it's a recapitulation. Now I told you that my greatest type of humor is to add zeros, and in my pocket I have many zeros. So here, observe, is now another 0. And again, I can do the same trick, move or change the parentheses, and then you arrive at expression. And again, expression that tells you how much there would have been changed if only set changed, and here if only Leontief inverse changed. So now we have two independent, separate things. What I said, hilarious, different 0. And now we have two different expressions for decomposing the change in outputs. But observe that again, the idea, the cause is changes in final demand, and in this equation they are weighted with the Leontief inverse in period 1, and here they are weighted with the Leontief inverse in period 0, and vice versa for the final demands. Now here in this simple case, this is the simplest possible case, but it tells you already all the problems. We have two different expressions for the change in output, and we cannot choose. We don't know, there is no reason to say this one is better, I prefer this one more than that. So they are equal to each other, and this is the famous non-uniqueness problem. And the solution here is take the average. And you can see that the delta F is here weighted with what you can call the midterm or the average Leontief inverse. And here the change in Leontief inverse is weighted with the average final demand over here. Some people do not like different. Well, in that case, it's given here. Here, the expression for delta F and delta has the same weights, period 1, and weights at period 0. But if you work this out, it means that the equal sign is only really equal if you take so-called interaction terms into account. And in this simple expression, I can think of an interpretation in terms of the amount in which these two changes correlate with each other, the way in which the two variables co-vary together. But that is doable for a simple decomposition with two components. But if you have three components, there are already four interaction terms. And the last interaction term is delta L, delta F, and delta something multiplied with each other. Now, go ahead and give me an interpretation for that. I find that very difficult. So, and if there are many more components, I get a whole truckload of these interaction terms. And I find it very difficult to give an interpretation there. So I do not like very much the interaction term approach, but it's valid. I mean, it's no problem at all. So this was the simplest case where we had only two components, the inverse and final dimension. Now we go one step further, and usually the step from 2 to 3 is an enormous step. It's much bigger than from 3 to almost infinity. So now we have 3 components. And here, this was already what we had. Now we're going to take the value added account. So we define value added coefficients as V, value added in industry I, per unit of its output in dollars. And we know that just for not to get stuck with all these accents, I've left out the accent here, but V is defined as a row vector of value added. So GDP is a principal row vector with value added coefficients times the total output, and using the expression for total output is Leontief inverse on final demand, we can write GDP as V L F. GDP is a scalar in this. Now we're going to look at the growth in GDP, the change in GDP, and we ask ourselves how much of the change in GDP is due to changes in value-added coefficients, changes in Leontief inverse, and changes in final demands. GDP period 1 minus period 0 is VLF period 1 minus VLF period 0. Now, these equations, these decomposition equations, often look terrible, and sometimes you think, my goodness, it's like a random generator that has been at work. Perhaps AI or ChatGPT. ChatGPT gave me a decomposition. Now that's what it looks like, but it's not the case. So I will tell you a very structural way of setting this up. So we're going from left to right, and later we're going from right to left. But now first from left to right. What do I mean? I mean that VLF, first I'm going to change V, then I'm going to change L, and afterwards I'm going to change at last the change in F. So let's start. So I'm starting here, and the first thing that I'm going to do is change V. So change V now into V0. V1, L1, F1 minus V0. This guy. Of course, here is a lot of space, and I told you, fun. We need to have a 0. Here is a 0. Because this expression doesn't belong here. It doesn't belong there, so I have to correct for that. So I'm going now to add here V0, L1, F1. See, this is the correction. And these two terms now express as 0. So still I have VLF at period 1 minus VLF at period 0. So this is 0. The next step is I'm going to change L. First the parentheses. Okay. So the parentheses now are here. The next step is I'm going to change L. So what I'm going to do is change L1 into L0. Change L1 into L0. So now we have a strange term. This one doesn't belong in this equation. So again, change something and correct, because it did this now at the moment, it destroys the equations. So again, correct. And again, observe that this is 0. And this was 0. Still, the whole expression is VLF at period 1 minus VLF at period 0. These terms are 0. Well, then, if you put the parentheses, and finally change F into F0. That's the last term. So that already has been done. That is what I mean with going from left to right. Change V, correct, change L, next step, make the correction, and then the last step is already there. So this is now the expression, and this is what we call, instead of going from left to right, we say it's the polar from left to right. And this suggests, of course, that there is another polar, and that, of course, is from right to left. Yeah, summarized, these terms are zeros, so the n is still VLF at period 1 minus VLF at period 0. This is the polar from left to right, what we've done just a minute ago. There is also a polar from right to left. So first change F, then change L, finally change V. Okay. This is what we start with, change in GDP, VLF in period 1 minus VLF in period 0. That's what it says here. And now the first step is going from left to right, right to left. It's change F into F0. That's the first step. This doesn't belong here, so again, you must correct for that. Add it again. The next step is change L1 into L0 and correct it because this term doesn't belong here. And then the final term is there already. Now we have here the change in F, the effect of change in L, and finally change in V. Observe again that these terms are 0, so the end result is still VLF in period 1 minus VLF in period 0. Any questions? Again, the non-uniqueness is, well, we have two polars from left to right and from right to left. We don't know which one to pick, and I love them both equally, therefore take the average. And the average is the answer. Well, I mean, have some fun. So you could make your own exercise, your own assignment. Take 26 matrices, multiply them with each other, and 2 times period 1 and period 2, and express the change in the matrix into the contribution by change in A, change in B, change in C, etc., etc. And well, I mean, it's easily done. I'm not saying you can do this in 2 minutes, but the principle is easily done. First change A, then B, then C, and every time you apply a correction, yeah, it gives you the result. And go from right to left. And if you do that, try this at home, certainly, and if not, send me the results, please. Well, I've done this course somewhere else, so I hear. Could have given, of course, the next slide, the email address of Jose Manuel. Yeah. You had a question, or you had a question? The other one. Here, the interaction here change. What do you mean? The interaction. No, there is no interaction. No, and the reason why there is no interaction is that, as you see, we have here different weights. So in this expression, delta V is the changes in value-added coefficients are weighted with L and F in period 1. Here, delta F is weighted with V and L in period 0, and the Leontief inverse is weighted with something in period 0 and something in period 1. And only if you do not like that, which is fine, you can have here L1, F1, here V1, F1, and here also V1, L1. And then you get 4 interactions. But since I'm a fan of zeros, but not a fan of interaction terms, so I don't give the expressions with the interaction terms. Okay. The blow up. Any other questions? So, well, it's great, excellent, and so far it has been hilarious with all the zeros, but only 2 polars. Life is not that simple. So we have done the polar VLF and the other polar FLV. Sounds intuitively, sounds obvious, but why not LVF or LFV or VFL or FVL? Who tells me that my choice is better than your choice? I don't know. No one. The only reason why I prefer this one is because from intuition, it seemed simpler to start from left to right and then from right to left, rather than this. It looked more random to me. But they are equally correct. So, polars are not more plausible than any other form. So therefore, I do not have a preference for either of the 6 forms. So all 6 forms are equivalent. So in general, there are n components, and the number of decompositions is n faculty. It's the number of times that you can reorder the n components. And the solution that we proposed is take the average, because I cannot make a choice between any form. To me, they're all equivalent. And in one of my papers, I had used 14 components. That's great fun, because that gives much more. That gives more than 87 billion different decomposition forms. So if you have to calculate 487 billion different decomposition forms and then take the average, even with a computer, that takes some time. So the message here, the key message is life can be a real mess. Fortunately, however, the average of the two polars turns out to be the average of the n faculty forms. So approximately life is the same. That was the key message in a paper that I wrote in 1998, together with Bart Loss, on structural decomposition analysis. Then in 2001, Javi Gahan published a comment or a follow-up, and he said, well, you don't need to look at the two polars. Actually, any two mirror decompositions give you an approximation of the average of both. So pick any decomposition, take its mirror decomposition. I will tell you what that is in a minute. Take the average and find approximately. So for the polar DLF, this is the expression that we've seen. That was the first polar. And the mirror image is obtained by changing the time indexes. So 1 becomes 0, and a 0 becomes 1. 0, 1, 1, 0. 0, 0, 1, 1. That is called the mirror. This is the mirror image of the polar. But here now we have widow. So LFV. So start with changing with start with V1 L1 F1 and start by changing the L1. That gives you delta L. Make the correction. Correction would be V L0 F1, and then change the F, and that gives you this expression. And finally, you have delta V, which is weighted with L and F here at 0. The mirror decomposition, change ones into zeros and zeros into 1. 1, 0 becomes 0, 1, and 0, 0 becomes 1. And you see this is exactly the mirror decomposition. It's going from V. That is how you calculate the mirror decomposition. Observe that we've considered so far additive decompositions. So, for example, the typical outcome, the change in GPP is 67. And the contribution by changes in value added coefficient is 13, changes in Leontief inverse 42, changes in final demands 12. What people often do is not look at the total, but look at the percentage contributions. And then simply divide 13 by 67 to arrive at 19.4%. That's what typically is done. So that was the basics. Any questions on the basics? Now we go to the extensions. And there are several extensions that I want to discuss. Dealing with constant prices, a multiplicative structural decomposition analysis. Something that is found in the literature now and then is the so-called hierarchical or nested decompositions. I'm going to look at changes in production structure. What is nowadays with the availability of these world input-output tables, these intercompany input-output tables, what is important to take changes in the trade structure into account properly. And finally, there's a problem if the determinants, the factors are dependent. They're not completely independent. Yeah. So chaining Here's a simple example of chaining. Now I'm going to look only at one polar, and the story remains exactly the same if we take the averages of two polars or mirror frequency. But here I'm going to look at the polar from left to right. And suppose this is the end. Changes in the change in GDP from year 0 to 1 is 70, and that is due to 40, decrease of 60, and an increase of 90. And in percentages. Now suppose that in year 2, or between year 1 and year 2, GDP increases by 10, and it's distributed 10, 20, and minus 20. Now, if you add the numbers that is chaining, then you get that the difference between GDP in period 1 and in period 2 is 80, and the contributions of delta V are 50 and minus 40 and 70 of the contribution for delta N. That's great, that's fun, that's leads to very nice graphs. So here I have the total, the increase of 70 in the first year and 10 in the second year. And here it's the numbers. You can see that blue, red, and green. Fantastic. And correct, no problem at all. But you should realize that be careful. So the delta V or the delta L or the delta F effect differ from the effect in a direct SDA. So a direct SDA would look at GDP2 minus GDP0. In that case, the delta V effect would be change in V weighted with the weights in periods 2. So there is a difference. There's a clear difference between V2 minus V0 L2 F2 and the summation of these two. It would be pure coincidence if these two together, taken together, were exactly the same as this. So chaining is nice, leads to beautiful graphs, fantastic, great, no problem, but be careful. Chaining sometimes is necessary. For example, if you are working with constant price, necessary in the case of constant prices. Now, suppose that you are interested in the increase in real GDP between 2012 and 2000. Now, this would be the decomposition form, one of the polar forms, if you look at the whole period. And in that case, and this is a valid form, no problem. For the result for 2012, what you use is the input-output table and constant prices of 2000. For the year 2000, the F for 2000, the L for 2000, you take from the input-output table in current prices in 2000. So it means, or you can take, in any case, take a table in constant prices. So in that case, the delta F reflects volume changes. So because the prices here, the prices remain the same. So what you measure in between F 2012 minus F 2000 is a volume change. And here also, it's a volume change because the prices do not change. And the base year is irrelevant. If you want to, you can take a base year of 1925. In principle, that should give you the same. The crucial thing is that if you use tables in constant prices, work with tables in constant prices, the delta F and the delta V and the delta L are based on volume changes. And here I highlight the delta F effect because V and L are coefficients. This one suffers from price changes. We'll see an example a little bit later. There's one problem, and in particular, if you work with these world input output tables, is that tables in constant prices often do not exist. Often you do have, however, information on prices, very often per industry in different companies. So the easy way out is to think, okay, easy peasy, I can make the input output table in constant prices myself. You take the prices and multiply all the rows with the price index. This is called double deflation. If you do that, then all the little errors end up in the sink. And the sink is the value added. Because, the input output table is a closed system. The output in constant prices that is listed here must be the same as is listed there. And in that case, if you multiply every row with products with the corresponding prices, well, then there is one row left for which you have no information, and that is a row with value added. And if you do that in a world input output table, then I can guarantee you that some of your values added will be highly negative. Now, there are cases where value added can be negative for some industries. For example, if an industry is heavily heavily subsidized, because part of value added is taxes minus subsidies. So if an industry is heavily subsidized, it can happen that value added is negative in that industry. But I can guarantee you that with double deflation, you get many more very, very funny negative answers. And this is a problem that everybody has, all the people who make these tables. And everybody has tried to make these tables in constant prices. And some succeed, or they produce results, constant price tables that still look okay-ish, but I don't know how they were made. So what we did, we said, okay, maybe part of the reason is that these years are pretty far apart. That could be a reason. So let's try to do exactly the same procedure as I told you just a minute ago, double deflation, year by year. And that is what, in our case, are the input output tables in previous year's prices. And if you use the wire database, they are given. So in that case, you do not run the calculation between 2012 and 2000 in one go. No, you split it up in 12 small changes. And for each of the small changes, you do the decomposition with the corresponding table in constant prices, namely the prices of the previous year. So if you look, well, let's again look at 2012 and 2000. Well, the first step is look at the change in GDP between 2012 and 2011. Now, one of the polars gives you 2012 here, change V. So V now becomes 2011. Final demand remains 2012, then change L, and then both become 2011. That is the polar decomposition. Now, in implementing, running your calculation, you use for the values for 2012, you use the input output table in previous year's prices. So in constant prices of 2011. And for the values in 2011, you use the table prices last year's table. Table of 2011. So in that case, example, the delta F prices remain fixed. Talking about final demand measured in prices 2011. So delta F reflects exactly what we want, volume changes. Well, the next step is between 2011 and 2010. Well, the same formula is different, and for 2011, you now use the input-output table in prices of 2010, and for 2010, you use the table in prices of 2010. That is then the table in current prices. Now, in this case, delta F, because everything is measured in prices of 2010, delta F reflects again the volume changes between 2010 and 2011. And have some fun between 2010 and 2000. This is the last one. And then change the results. I have worked this out, so we have a delta V effect, which consists of 12 terms, and we have the delta F effect, which consists of adding 12 terms. And here is worked out the delta L effect. So the delta L effect between 11 and 12, between 10 and 11, etc., etc., etc. So yes, this is a bit of and if the table in constant prices would be available, this is your answer if you use the table for 2012 in constant prices of 2000. Now the advantage of this using a table in constant prices is less work. So more time for coffee, mezcal, or whatever, which is very important. But there are some disadvantages, and of course, the disadvantage of one method is the advantage of very often of another method. The point is that in the red table in constant prices, well, very often these constant prices are based on a basket of goods, and the goods is they calculate the prices, the average prices in 2000 for a certain basket. But the basket of goods changes heavily between years. And the further apart the years are, the larger the changes will be. So, for example, it may be the case that the final demand in 2012, the prices for that may include products that even didn't exist in 2000. I mean, look at simple things like tablets and iPhones, etc. I mean, there was a time that people said, well, 10 years ago, it didn't exist even. So then you are working with the price of a basket of goods that is completely outdated. So that is a huge disadvantage if you use the simple method. And that is the advantage of the method in green. It changes the basket of goods, composition of the basket every time. I think that is an advantage. So even if tables in constant prices are available, I think this would be a better method, because it takes account of the slowly changing composition of battery. Well, great fun, but this was an example about GDP. Could you do this same analysis with tables in current prices? Yes, you could, because I know exactly where the crucial mistakes are. And I used tables in current prices, so not taking any constant prices into account. I can tell you that here I made a mistake, and here also a little mistake in value added coefficient. The mistake that you make here is very small, it's usually negligible. And why? The easiest way to see that is, and that is also the case when I think you must use constant prices, is when there is a mix of physical and monetary tables. So suppose in this case, we have the employment in hours, then that would have been an issue. Or here, instead of employment, we now say we have greenhouse gases and indicate them with a G. G is the emission coefficient given the greenhouse gases in tons per dollar of output. And you have the dimension is ton per dollar. So the total amount of greenhouse gases would be G times X in this country, so a territorial emission. Using X equals LF, we now have, instead of GDP, we have greenhouse gases, it's G times L times F. So instead of what we did on previous slides with a V, we now do on the next slides with a G. Now, assume nothing changed physically. We blow up the same amount of greenhouse gases into the air next year as well. The only thing that changes is that the prices change. So physically nothing changes. In that case, the amount of production, for example, in liters, meters, kilograms, and the amount of emissions are exactly the same. Now look what happens to the emission coefficients in the input output table. The MI, that is the emissions itself, because GI is the emissions divided by the output, that will be the same. Because I told you nothing changes in terms of emissions. What does change, however, due to price changes, is the X. And suppose we have serious inflation, the prices seriously go up. That means that your emission coefficient will decrease, whereas nothing has happened physically. Okay. So, is that here? No. So let's go back here and assume we should have written a G here. Now, this delta G is misleading because you think that it has gone down, whereas nothing has changed. At the same time, the delta F in new prices has gone up, whereas physically nothing has changed. So if you apply a structural decomposition analysis to decompose not GDP, but the increase in territorial greenhouse gas emissions, I can guarantee you that this term is largely overstated, and this term is largely understated. This is too big, that is, this is more or less the same, because these are coefficients based on input coefficients, and the input coefficients are dollar per dollar. And it doesn't matter too much whether it's constant dollar per constant dollar or current dollar per dollar. That's okay. There is a difference, but it's not that important. Mistakes are here and yeah, so the conclusion, if you are running an analysis where you mix physical and monetary variables, then be careful to use tables in current prices and use tables that reflect volume changes. That is very often what you're interested in. So work with tables in constant prices, or preferably work with tables in previous year prices and change results. And if you ask for my preference, I think this is preferred. I prefer this because the weights changed, and that is reflected in PYP. Suggest that we have a break.
No, se apagan el micrófono y cámara, la dejan así. Pero sesión, apagan el micrófono.
estos años a ver si los supongo que ya veo el listo para detalle. No puedo.
If you agree, I will continue.
Yes.
If you disagree, I will still continue. As I say. But I can continue and start to. Usually we have.
When it's happening.
Yeah. Excellent. Good. So in general, if you do look at the growth of ratios, you may want to look at multiplicative SDA. Now, well, apparently, if you touch something there, touch the screen, and then you continue working. Okay, yeah, that's it. Good, thank you. So here we now have consider simply the growth in GDP. And suppose that you want to, because the growth is usually given in percentages, and therefore you want to analyze this. I told you that the biggest joke, I think, is adding a zero. Here, I don't need to add a zero, but I need the multiplicative same kind of thing, and that is multiplying things with 1. That is the same thing. So, you know, a 0 multiplied by 1. So I start here in the numerator, and V0, L0, F0 is somewhere over there in the denominator. Now, the first thing, I'm going from left to right. So I now change V1 into V0. I change V1 into V0, but immediately must correct that because this term doesn't exist here. So I've now multiplied it by 1. And we're all laughing, this is hilarious, but it is correct. And the next thing is I'm going to change the L1 into an L0 and immediately correct that. So that yields another 1. And now observe that these are the same except for the V. These are the same except for the L. And these are the same except for the F. So this term, gives you the changes in V. This term gives you the changes in L. And here the changes in F. If you use colors, like this, and of course now you regroup them, red above red, green above green, and yellow above yellow. And this gives you in a multiplicative case, the polar from V to L to F. Of course, no. It's the polar. And for example, the typical outcome is 1.50 is 1.25 times 1.60 times 0.75. And the interpretation is if only the value-added coefficient had changed and the rest would have remained the same, it was power bus, then GDP would have grown by 25%. And if only the Leontief inverse had changed and the rest had remained the same, then GDP would have increased by 60%. Here, the value-added changes would have led to a decrease of 25%. And multiplying these terms with each other gives you a total increase in GDP. This example, 50. So this was the polar from left to right. The polar from right to left is F first, then L, then V. So change first, well, get them apart, and first change the F1 into an F0. 1 into F0, and correct for that. The next step is change L1 into L0 and correct for that. I'll put the colors nicely on top of each other, and you arrive at this. And this is the other polar decomposition. And instead of the arithmetic average, half of this plus half of that, you now take the geometric average of the polars. And if you do this for x, so x equals L times F, then you have something that looks very much like a Fisher price index. For those of you who are into price indices. So this is how multiplicative SDA works. Actually, it's very similar to additive, but instead of adding zeros, you now multiply everything with one. Any questions on that? The multiplicative SDA? If not, we go to hierarchical decompositions. Sometimes you see them without people using the term. I've also seen it, people using the term nested decompositions. But I think my colleague Jan Oosterhaven and Jan van der Linden, our PhD student, and later with Alex Hoen, another PhD student of Jan and myself, they developed what they called, think they were the first ones, and they called it hierarchical decomposition. Let's take a look now, something slightly more complicated. So we have a final demand factor, and it consists of 4 terms. So we have household consumption, private investments, government expenditures, and export. That's the national final demands. And suppose I'm now writing total consumption, adding all the elements in the consumption factor. That gives you CT, where T stands for total consumption. And we have consumption shares, which is simply consumption divided by the total. So you have a factor of consumption share, and they add to 1. I think there's the next example on the next one. And you do the same for private investments, for government expenditures, and for export. So here is a simple example. We have a vector of consumption, a vector of private investments, government expenditures, and exports. This is the total final demand. And here in this row, I could have used colors here, and this row gives you the totals. PP, PT, GT, and ET. Now, F is the matrix with shares. That is 100. 100 divided by 900, 0.11, 200 divided by 900, and 600 divided by 900. So these are the shares. And the shares for private investments, 40 divided by 90, 20 divided by 90, 30 divided by 90, etc., etc. Observe that the shares add to 1. And these are the totals. Now, in that case, I can write final demand here, 190, 290, and 830, as the matrix F times the totals. Because if you do the calculation, 0.1 times 900 is the same as 100 divided by 900 times 900. No surprise that is 100. So it gives you the total final demand. You also agree?
What is la última columna?
Yeah,
De
that's
las
here. This one.
90,
900.
this?
Look here, look here, look here. This column is the totals. Oh. If we agree. Now, so we have the GDP is V times L times the final demand vector. But the final demand vector, I now write as F times T. So the decomposition becomes a little bit more complexer, larger. The polar decomposition change V, L, capital F, and T. This is the other way around, so the other polar. So this is the average of the two polars. So this is just a standard structural decomposition with 4 components, and there's nothing hierarchical at the moment. So this is a valid decomposition, no problem at all. This is what we've done in the first hour, but now with 4 components. Now, I'm going to talk about the hierarchical decomposition, why the hierarchy is. So we start with GDP is VLF. That's one level, one nest. And then the next level, and that is the next level of in hierarchy, is split the small f into capital F times T. So this is now decomposition for 3 terms. VLF. And here you have the decomposition, something like what is there for F capital F times T. And the hierarchy is now plug this expression in here and here. You see, that is the hierarchy. So this delta F now consists of a red and green part. This delta F also consists of a red and green part. So now the answer would be again 4 expressions. Take the reds together, take the greens together, the blue and the yellow remain as they are, and this is the hierarchical decomposition. You see? No. Okay. And if you at home later, after I've made the PowerPoint available, you can check that this is a different decomposition. It looks different, you have slightly different answers than this decomposition. These decomposition, hierarchical decomposition are found, no problem at all. In some cases, it may be useful. Suppose that you are studying something and you want to study in more detail because you have more information. What happens to delta F? Where does delta F come from? And suppose you have information on label changes, capital changes, tax changes, etc., etc. And suppose you have some information why L changes. It becomes of this and that and whatever. And you have information like here on how small f changes, shares and totals. Now, if you can combine everything in a big decomposition, you can also say we have a relatively simple decomposition. These are the results, and V counts for 40%. And in the next step, or delta F counts for 40%, and then in the next step, you further split that up. In that case, hierarchical decomposition can be very nice. Then, production structure. So far, we have discussed only changes in L, the Leontief inverse. So that is I minus A inverse. Well, you do not change L. L changes, but it doesn't tell you very much. So the question is, where do the changes in L come from? Changes in L come from first changes in A. But it's much more convenient, as I will show you in a minute, if you want to talk about changes in the production structure, to have an expression that gives you delta A and not delta L. And this is the way how to do that. So simply consider the expression L1, A1 minus A0 post-multiplied by L1. And again, add some zeros, write A1 minus A0 as I minus A0 minus I minus A1. I's fall out, and you have here minus A0 minus is plus A2. So that's exactly the same. Now split the two, L1 times L0, L1 times L0. That's what it says here. Now observe that these two together are the identity matrix, and these two together are the identity matrix. So this exactly is L1 minus L0. So I can write delta L now as L1 times delta A times L0. Mathematically speaking, it's exactly the same. The derivation is exactly the same. You can write it also as L1 times delta A times L0 times delta A times L. Whoa, congratulations. So the question tonight is, what did you do on Friday morning? Well, we did some terribly boring matrix algebra, good for my second year in math, but so what? Well, so what? I can tell you that this is where the action is. And the action cannot be translated easily into where changes in delta come. So, for example, suppose you're French and you're interested in what are the consequences of all the changes in the production structure, in the production recipe of steel manufacturing. How much has that contributed to whatever it feels? Well, in that case, here you are. You now have delta A consists of delta steel manufacturing and delta yellow. So you can split the delta A into a delta exactly reflecting what you're interested in, and the other changes in A. So that is why this is useful. Or if you're interested in substitution, replace green by red. The delta A now splits into delta green plus delta red, or delta green, delta red, and the rest. I don't know. If this is what you want, go ahead. It's possible. You can change the delta A into delta red, delta yellow. And of course, the interpretation here is so whatever you want. I've seen people or students ask me, is it now possible to have and the changes in industry 1, changes in industry 2, 3, 4, 5, and 35? Yes, it's possible, but you get a very big structural decomposition in that. So, and that is the issue here. A lot is possible, so you should think beforehand what you want. And then that should be in your structural decomposition. Then trade structure. I'll do this also with an example. So we have 3 countries here, red, green, and yellow. And these are the input coefficients. So they come straight from multi-regional input. What we're going to do is, what does this tell you? This tells you that in industry 1 uses inputs from country itself, uses inputs from country 2, country green, and from country yellow. Now, how much inputs, suppose we have agriculture and manufacturing. How much agricultural inputs are used here? It's 43 plus 3 plus 5. That is the first. Technologically speaking, the amount of agricultural, industry 1, agricultural inputs that are needed in the first industry in red are 0.5, 0.8, 0.51. That is the technical requirements. And then the rest is simply splitting the technical requirements over where does it come from. Coefficients I call Q. So that is the 0.51 that we saw just a minute ago. And 0.6 plus 0.4 plus 0.10 is 0.20. That is how you calculate this Q numbers. And here you now have pairs. Where am I going to start? 0.43 divided by 0.51 is 0.87. Second, 0.03 divided by, talking about agricultural inputs, 0.51 is 0.05 divided by 0.51 is approximately 0.1. So these shares add up to 1. So the key message is, take another color. Second industry, manufacturing, in country yellow, requires, technically speaking, 0.14 inputs from agricultural inputs, not knowing where it comes from. And it requires 0.45 inputs from manufacturing, technically speaking, not taking into account where it comes from. Now, here, the 0.14 agricultural inputs technically into yellow manufacturing is, of these 0.14, 7% comes from country red, 50% comes from country green, and 42% comes from country yellow itself. That is how this should be. And this is the technical input coefficient matrix, and this is the matrix that reflects the trade stock, where the diagonal blocks indicate trade with your own country. That will be the domestic deliveries.
Question. It is the technical coefficient of this one country or the countries is different. Is supposed that they have a different technicals of production?
No. Here, this is the underlying assumption in the input-output analysis. We assume steel is steel. Full stop. Mexican steel is Dutch steel is where. So the point here is we require so much. Well, this is agricultural. This is steel. We require 0.2 steel. Full stop. We don't care where it comes from. And only here, this color, we start worrying, observing so much of the steel that I require comes from Mexico itself, so much from wherever. But yes, the underlying assumption is steel is steel. Otherwise, you will not add these. Well, basically, this is what I said. If you have time, you can read it later. So let's take, again, portfolio decomposition analysis, and suppose we're interested in GDP. So we have one of the terms, the delta L effect, is V0 delta L times F1. So what I'm going to do now is I'm going to substitute delta L, this expression that we derived, the matrix expression that we had earlier, into delta L. That gives me something like V0, L0, delta A, L1, F. That is, and you have the information, you have the numbers, so you can fill the numbers in here and there. Now the A, that is exactly what we did here, is that this A actually is multiplying, or actually dividing these technical coefficients into the shares. And I write that as S times Q, but using the element-wise multiplication. Actually, this is incorrect. If you do that, you should have a super Q. So actually, the correct would have been and as you see, this is a 6x6 matrix, and now 3 Qs, the same Qs on top of each other, are now also Can you see? And now also the story that is not entirely clear. Well, then you have, I can do the structural decomposition analysis on delta A itself. So that means delta S times Q1 plus S0 times delta Q. And this is the other form. Now, if you implement that into, not yet, if you implement that into here, then you have the effect of technological changes, technical input coefficients. And this term, if you put it in here, reflects changes in the trade structure. And as we will see later in the applications, we use the World Input Output database, and we're interested sometimes in the role of China, and we see that all countries all of a sudden stop using and buying European inputs and replace them by Chinese inputs. That is measured in this delta Q because these import shares from Europe, they decrease, and the import shares from China increase. The effect of that can be measured this way. That is measuring trade structure changes. The last issue is a nasty issue for which we do not have a real solution. We have a kind of a solution, but it's not a beautiful one. So just for simplicity, assume a closed economy. So there are no imports here involved. We have intermediate inputs and value add, and that's it. Or no, that's take it to them. And the GDP is then Vx, where V is the row with value added coefficients, W divided by X. So GDP is again V times L times F. You run your SDA, and the change in GDP is expressed in this way. Congratulations. 1, 3. This term here. Interpretation of this term is what would have been change in GDP if these value-added coefficients had changed, and the rest remained exactly the same. This case, if value-added coefficients change, it's impossible that the rest remains the same. Because look here, in a closed economy, and the same holds slightly different way for inputs are included. These two together, add them up, give you the total outputs. So if you divide the Z by X, you get an A. And if you divide the W by X, you get a B, which means that A plus B must add up to 1s. So the value added coefficient is by definition, by construction of the input output table. Otherwise, you fucked up the whole input output table. Your consistency is gone. So this must be true, full stop. No arguing. So Vj in this setup is 1 minus the sum of the input coefficients. So if you change Vj and claim that L or whatever, L has remained constant, implying that A has remained constant, that's not possible. Because the sum of the A's must have changed as well. So that is where the problem is. So we have constructed a structural decomposition where components are not entirely independent. So I can simply not say that change one thing under the ceteris paribus clause that the rest remains the same. And the problem is you can run your calculations and you get the numbers. And you don't see, from the numbers, you don't see that there is something strange going on. So this was an extreme example. An example where there's full dependency between two of these components. We have written a paper about this in 2000, Bart, Loss, and myself. And well, the SDA assumes that these components are by definition independent. So the idea is change one component, and then you assume that the rest remains the same. And sometimes that is not possible. And actually the SDA needs to be adapted. In many cases, some form of dependency exists, but not full dependency. And we adapt the SDA, but it has implicit consequences. So for example, previous slides were for the closed model. Suppose you have an open model, then it's not only value added, but it's value added plus imports. So implicitly, you can say, assume that the value added coefficients change, assume that the A coefficients remain exactly the same, then actually you are saying implicitly, I assume that import coefficients are exactly the opposite of the change in the value added coefficient. But as long as you do not do anything with the import coefficients, that's technically possible. In that case, this is often a way out. Yeah. So you have the sum of V plus the sum of M and W must be exactly to the outputs. So we have here now that value added coefficient equals 1 minus the sum of the input coefficients minus the sum of the import coefficient. And as long as you're not going to do something with the import coefficient, you can always say V changes, A remains constant, hence implicitly message is the B's change, the input coefficient change. But if you're not interested in the B's, who cares? Technically it's possible. Yeah. If you're not happy with that, or in some cases that is not possible. I mean, if you use a world input-output table, you have no imports, so there is no row matrices that rescue you from this. So you have to come up with something else. So we proposed something in our paper. I think that's too technical to deal with here right now. You can also use a different methodology. So for example, also structural decomposition analysis have been developed based on a logarithmic mean divisor index decomposition. Now the matrix analog is also available, is stoppable, and this decomposition does not suffer from these dependencies. The one big but here is that this is much more difficult to apply than the simple structural decomposition analysis. So there is a price to pay. But that is your choice. Careful. Because this is you don't see. You don't see that possibly your answers might be slightly misleading. The numbers don't tell. You want to take both right now, or yeah, I know that's the easy way out. You are nodding yes, so yes, he's the one. Yes, yes. Dit in video? Yes, please. And also fill and chat? Goodbye.
Ya, ya.
Yo confiaba.
Y presentó un cuate.
Ah,
Pues,
¿mandé?
Okay. Discord at least. So it's here application, and I'll go through three applications. First one I did with Iñaki Arto. It's and published in 2014. It's a little bit old, but we will continue on these results. In a minute, I will show you updated, slightly different decomposition and the results for a different time period. Here we look at 95, 2008 or 9, and then we look at 2000 to 2014. And some remarkable changes have taken place in just shifting this period, this time frame by 5 years. So looking at 95, 2008, we're looking at global greenhouse gas emissions, and they increased by almost 30% by 8.9 gigatons in this 14-year period. And our questions were simple. What drove the growth in global greenhouse gas emissions, and in particular, which countries? Who is to blame? Of course, it's all of us. So at that time, in recent years, growth in emissions from the production of traded goods increased tremendously. So emission transfers through international trade. There were papers by Glenn Peters and friends that used the GTAP database, and they ran calculations calculating the CO2 that was embedded in trade. So it's slightly different from footprints, because then you're not only interested in CO2 embedded in your trade with other countries, but you're interested in a footprint in my CO2 that is embedded in your use of final products. So the trade in the emissions in the exports are different from the exports in trade. It's very confusing terminology. Well, the idea is simple. Suppose we don't like each other. We are at war. So you and I do not trade with each other. So I have no exports to you. In that case, obviously, there cannot be any emissions in my exports to you, by definition, because there are no exports. But we do have friends, common friends, with whom we trade. So it is possible that my emissions end up in your consumption pattern because we trade with a common friend. And that's the difference between emissions in exports, 0, and exports of emissions. That is possible. I think nowadays they use in particular GTC exports instead of the confusing terminology, trade in exports or exports in, emissions in export or export of emissions. But to always be clear, read just the abstract and the introduction, go to the model to find out what exactly have they, particularly in the older papers, what did they calculate. As a matter of fact, even the TIVA database, trade and value added, I think does not cover trade and value added. It covers value added in trade. Meaning no trade, no value added in trade. So there's a lot of confusion. Argo and some of his other friends, I was not involved there, he used the WIRE database, found that the greenhouse gas embedded in trade increased 90% from 95, no, sorry, increased from 19% to 27%. And Graham Peters and friends found something similar for the GTAP database. So this suggests that trade has increased quite a lot, so therefore more emissions got embodied in trade. So more trade costs more global emissions. And the idea was that this process could have contributed to global increase in global greenhouse gas emissions. First of all, through the delocalization of the dirty industries. We've talked about this, the pollution haven idea, poor and richer countries, but also through higher emission intensity. I mean, if the problem is if you delocate to other countries, it could be possible that you delocate to countries that have higher emission intensities. So the third question that we try to answer here, did changes in trade structure contribute to the growth in global greenhouse gas emissions? And these are the results. So in 1995, the greenhouse gas emissions were more than 30 gigatons. In 2008, 39 gigatons. So the increase, that is the purple line, is almost 9 gigatons. Affluence is means eating more per person. So this is consumption per capita. So it's increase in household consumption per capita. That on its own would have increased global greenhouse gas emissions by 14 gigatons. Happily, the technology improved, emission intensities in general decreased, and that led to a total decrease in greenhouse gas emissions of 8.4. Population, the fact that there are more people on the earth than before, and everybody has to eat to stay alive, increased greenhouse gas emissions by 4. So observe that together, eating more per person, more persons together, that would have led to an increase of 18 over 30 is 60%. And of course, we all get richer, and so at a certain stage, developing countries get more and more developed. Particular 1.3 Chinese people who become a little bit more wealthy, start driving cars, etc., buying air conditioning, and then you see what happens. Trade structure that was implemented in the same way as I told you in the previous hour. The influence of trade structure, changes in trade structure, was only 0.6 gigatons. So hardly any change, hardly any effect. And the same for the changes in the composition of the final demand. So it could be the case that people buy more emission-intensive products or less emission-intensive products. So all in all, this was a small component. Observe that the developments were relatively low and slow, very flat until 2002. Yeah, so 2002. And there is, of course, with this analysis, there is no way to measure causal effects, but I wouldn't be surprised if the accession of China to the World Trade Organization is behind this booming business. So here are the results for the details, and now for the countries. Now let's take China as an example. So the numbers that you see here add up to a total of 2,766. So that is approximately 2.7 gigatons. What does this mean? Changes in China have caused global emissions to increase by 2.7 gigatons. And that is 31% of the total increase in global greenhouse gas emissions. And what caused this number? Well, observe here that the Chinese, we're always talking about the Chinese, and sometimes even about the dirty Chinese when we're talking about emissions, but they have done a great job. So they improved already quite a bit of their dirty coal-based power generation. Improving their emission intensities led to a decrease of 2.5 gigatons globally. At the same time, China became also more wealthy, and the change in their consumption per capita increased global emissions by approximately 5 gigatons. So that is how you should read the numbers. Mexico, as you can see, is a pretty boring country. Nothing going on. No colors in Mexico. I mean, there is enough colors already on the street, so don't worry. What is surprising, though, is that given the size of Mexico and Mexican emissions, this number is not very high in comparison to the other numbers. So I think in the years 95, 2008, I think Mexico, if you compare this with what the other countries do, Mexico could have done a better job in improving their emission intensities. The rest of the numbers are normal. Very surprising is that, well, the BRIC countries, extended with Indonesia, they did not have much growth in population, but the Americans apparently will. They do. So they have apparently created lots of babies that keep a whole lot. Babies. Okay. So this was the number 2.7 gigatons, the 31%. It's purple now because I'm going to use these numbers again. That's why I highlight them in purple. Here they are. So we have two bars. We have the gray bar that gives you the total amount of emissions in China, the territorial, or actually the change in the territorial emissions. And the change in the territorial emissions was almost 4 gigatons, and that will be 44% of the 8.9 total change. The country changes, or the global changes in global emissions, for which China is responsible, or which is due to the changes in China, or the Chinese emission intensity changes in Chinese consumption, that is in the white column. and that is the 2.8, 2.7 gigatons, which is 31% of the total change of 8.9. Difference is indicated here, and that is 1 point something. And that indicates, well, the difference between, actually, this is the territorial emissions, and these are the footprint emissions. So this indicates that China emits on behalf of the rest of the world. And this is the USA is here, and you see the USA and in particular the European Union are net importers of emissions. And so is Mexico, so is Canada, even Turkey and Australia. The others are exporters. Well, here's the difference between Brazil, Russia, India, Indonesia, and China, rich countries, and developed. This is the well, not a follow-up, but this is a similar decomposition analysis that I did with Victoria's, and the paper is under to revise and resubmit. And also here, the question is what drives the development, but now in global CO2, only CO2 emissions. And the idea is increased affluence, as we saw in the previous presentation, consumption per capita, and the technological changes decrease. So what we find is that between 2000 and 2014, the growth in CO2 emissions, we're not talking about greenhouse gas emissions, numbers are slightly different, not entirely comparable, but the effects are almost 11 gigatons, and the role of increased affluence was 14 gigatons, technological changes, and all the other drivers together are approximately 6 gigatons. So that was the point, increased affluence is stronger at the global level than technological improvements. Fine, congratulations. Similar outcome as in the previous slide. But now we'll go to the country level. And here we'll also take the country level into account. So does the conclusion that increased affluence is stronger than technological improvements, does this also hold at the country level? And that is a valid question because our countries do not develop at the same pace, as we will see. So countries are in different development stages, and well, it depends where the country is, because we have here the environmental Kuznets curve, and it's an inverted U shape, and here it says per capita income, and here the environmental degradation. So very poor countries, if their per capita income starts increasing, then the first thing you do is adopt eat more. Buy also go to McDonald's now and then, do some luxurious things, and only after that you start worrying about the environment. So the first thing, if you're from very poor to developing a little bit, no wonder you see that emissions increase, basically because people start consuming much more, enjoying their wealth, their additional wealth. Only after a while, where the relatively high per capita income, you start worrying about the environment. That's what you see happen now in China. All the people with, in particular with little kids, they try to leave the cities because the cities are extremely dirty and it's unhealthy for their little children. And the little children are everything to them, so they go out. Only after you have reached a certain point, you start worrying about the environment. Yeah. And here it's also related to the literature on decoupling. So there's relative decoupling in the flattening part of the Kuznets curve. It's still increasing, but it's increasing slower. And there is absolute decoupling if negative when there is negative pollution growth. So in general, the key question is what drives developments of global emissions at the country level, and you can choose for two perspectives. You can look at the territorial emissions and the global drivers. So it tells you how much US emissions are affected, for example, by global population changes. Or you can, the other way around, that's what we also did in the previous paper, look at global emissions and the national drivers. So how much are the global emissions affected by changes in US emission changes? And that is what we're going to look at also in this book. So here we use structural decomposition again. Now we use the Wyatt 2015 release. So the time frame shifts a little bit. We now look at 2000 up to 2014. We use Wyatt because the tables in previous prices are available, which is crucial because we have affluence, which is influence affected by price changes, and we have emissions per dollar of output. And because the value of the output is affected by price changes, these coefficients are also, these intensities are also affected by price changes. The database now has 43 countries plus the rest of the world, and slightly larger number of industries, 52. So these are the elements that we take into account, largely following what I showed you in previous hours. We have technology, that is huge changes in the emission coefficient. We also have something similar for, we also take into account here the emissions directly by households, so driving a car, and we have also there a technology component. We have the trade structure matrix that I explained earlier. We have the mix in products and inputs. We have affluence and population. At some stage, we're also going to split the technology, the changes in emissions per unit of output, emission coefficients into domestic and foreign. And for trade, we look at the shares from the source countries for inputs and final demands. Mix, what we said is the composition of the bundle of inputs and final demands. Affluence changes in not only household consumption, but final demands per capita. I'm going to split them later into households, investments, governments, and all other foreign components. And of course, population here. And these are the results. So the CO2 emissions grew from 26 gigatons to approximately 37. So the increase was 11 gigatons between 2000 and 2014. The total is given in black. Number here is 10.8 gigatons. And the other lines reflect the components. So for example, affluence almost goes through the roof and ends here at 14.3. Population, 3.9. So together it's 18.2, an increase of 18.2. In comparison to the 25 would be an increase of 71% in 15 years, if only affluence and population had been the drivers. We're very happy to report that, again, technology has improved quite a bit, and happy about that because that decreased the global emissions by 9.2 gigatons. Changes in the mix were almost negligible, and the trade component is plus 2.4 gigatons. Recall, I think that's on the next slide. Yeah. Recall that in the previous analysis, this was 0.6 gigatons, but then for greenhouse gases. So that's a huge difference. In the previous, for the previous paper, I said the trade component is almost negligible, 0.6. Now the trade component is not negligible anymore. So in the previous paper, net effect was 0.6. And where are these effects come from in the trade structure? First, from substituting domestic products for imported products, and the second change is substituting imports from Europe, US, by imports from China, for example. So then it was a very small amount, and we said, okay, it does matter what you eat, or what is in your consumption profile, and not so much where you buy it. That has changed also in the new period. Because recall the genes that I mentioned on Monday, 65,000 kilometers going all over the world. That is typically something that started to take place after 2000. It's fragmentation and finding the cheapest inputs, no matter whether they came from the other side of the world or from your neighboring country. So here, the 2.4 in this study is not comparable to the 0.6 here, because this greenhouse gas emission is CO2, but we can look at the percentage. And here it's 22% of the total chain. And in the previous study, it was only 7% of the total chain. Now, two aspects here. The new window covers the boost in international fragmentation, the genes going all over the world. So value chains became longer, and other studies have shown that there's a peak in this traveling around the world around 2012. The other change is substituting European and US imports or import inputs for Chinese inputs. That is also what has happened. And Chinese inputs are made, well, whenever they use electricity in those days, electricity was largely coal-based power. And that is pretty dirty. That is what changed, and that is what made these that caused that the trade effect changed in trade structure now are, well, considerable. Look at the results at the country level. So you should realize that these the numbers on the axis, the graphs are of equal size, but the numbers on the axis are different. So this graph goes up to here, 5 gigatons, and for India, this is India, only 0.5 gigaton. But it's not so much the size or the numbers that matter, it's the developments in comparison to each other. So what we see is that the developments are monotonically increasing. The red is almost going parallel. So affluence in both countries is substantial. And in India, we see an interesting increase in population due to population growth. And in China is technology. Chinese technology improvements would have led to 3.5 gigaton decrease only. So that is considerable. The graphs, the pictures for US and European countries are much different. They're hardly monotonically, it goes a bit up and down and all over the place. But you see that in the end, for the US, a decrease, a small decrease of 0.2 gigatons, in Europe, 0.6 gigatons. So Europe and the US did manage to decrease their footprint, not much, but a little bit, at least. So modest declines in footprints. In Europe, the numbers are now on the axis almost the same. In Europe, a substantial decrease of 1.7 gigatons. In the US, only 0.6, but in the US, apparently, they started all of a sudden to eat less emission intensive products. And for the rest, there are some positive for population and trade in Europe, 0.7. Now, this is a graph for the countries that are included. This is no, I can check. I think it was 5. This is oh no, it's 3.2. So this is China, the bar on the left. In 2000, it was 3.2. In 2014, the footprint of China was 8.9. So that's an increase of 178%. And that is the dot here. And we're working in this graph with percentages because we want to compare China with a country like Belgium or a country called Malta. Does anyone know where Malta is?
Somewhere in the Mediterranean.
Exactly, it's a drop in the ocean, well, not in the Mediterranean. I mean, it's nothing. So, but still, we want to compare these two countries of completely different sizes with each other, and that's the reason why we work here with percentages. At the bottom, you cannot see very well, but here are the countries. So China is on the left, and Greece is the most right country. What you also probably can see from a distance is that there are colors. There are 3 colors. So the red, orange is lower middle income. The yellow is upper middle income, and the green is high income countries. And you already see that green is concentrated on the right, red or orange is on the left, and the yellow is scattered all over the place with a concentration on the left-hand side. Mexico, according to, and these numbers came from the IMF, Mexico is listed here as an upper middle income country. Observe that 28 countries have their dots below zero line. So 28 countries decreased their footprint, and the remaining 16 countries, including rest of the world, increased their footprints. So given the fact that the global emissions increased by 42%, it means that the large countries, the large emitters, increased their emissions, and the small countries like the drop in the Mediterranean, Malta, Greece, and the Netherlands, etc., small emitters decreased their emissions. Also that on the right-hand side, with the largest decreases are the high-income countries, and on the left, the red and the orange are on the left. So on the left, we find countries like China, India, Soviet Union, and East European countries, where the affluence is dark red. So these typically are countries that over time in this period, they got a little bit more wealthy, and they were starting to use their money, to use their wealth by buying more products and buying a car, etc., etc. So the affluence is there dominant. In South European countries, you find sometimes below the zero line, here for Greece and Portugal and Italy, Malta, Cyprus, another drop in the ocean, Spain, you see that the dark red here is negative. So the affluence is even negative. And this is because the Southern European countries, they showed a very slow recovery from the global financial crisis. Europe, US, Japan, and Taiwan, their affluence is positive, but very, very, very moderate. So they have reached the stage where apparently it doesn't matter if you eat much more, consumption is not so emission intensive. And emission technology changes there were always positive, except for the case in Brazil. Looking at the details for a country, here we look only at affluence and technology. So components between affluence and technology are split into, the difference between the footprints for China in this case between 2000 and 2014 are split into affluence, technology, and the rest. So the affluence effect is 0.7, 7.8. And as I told you, we also split this further into household consumption, fixed, gross fixed capital formation, investments, government expenditures, and foreign. So this is the foreign use of final goods. The technology effect was a decrease in 3.5 gigatons, and the domestic technology would have led to a decrease in the footprint of 4.4. Foreign technology increased the footprint by 0.9%. So, and if you subtract these numbers, you see that there is also another component left over with all the others. We'll focus here on affluence and technology. So here you see the colors. Household, gross fixed capital formation, government, and foreign. And the same fashion here, technology, domestic technology, foreign, and this is the remaining, no, sorry, this is the summation. Now, these are the numbers, the graphs for China, India, US, and Europe. And observe that gross fixed capital formation, and again, the scales are different. But just look at the colors and size of the bars in comparison to each other. And you see that gross fixed capital formation investments is a substantial part of the affluence. So that is what you see in China. So they are building up their infrastructure, urbanization, and that is very emission intensive. A lot of cement is used and transport, etc. In the US and the European Union, see that the bulk of the dark red is household. Household consumption is the largest part of the affluence. So there the infrastructure and machinery is already in place, and the emissions due to extra household consumption, eating more, is not so large. The imports of final products is 10 to 20% of all the affluence effect. Observe that this is relatively small in comparison to the other red bars. So all the changes that affect the home products or use of home products are the most important. Looking at technology, you see that the technology improvement in China is very substantial. However, it turns out that the technology changes in the rest of the world had a positive effect on the Chinese footprint. So the point is that imports by China currently have technologically seen become dirtier. In India, you find very small effects for technological change, and in Europe, it's very large. In the US, however, you see a relatively large effect for the improvements of foreign technology. Yeah, they start importing much more from China that has improved its technology. Sorry, that's part. But the Americans themselves, well, very modest improvements in their own technology. In Europe, this is, and we will see that in the last paper, the start of the energy transition. Here again, the same picture now focusing on affluence and technology again. And we see that the technology effect, the blue bars are larger than the affluence bars, indicating a negative effect for most of the European countries, Korea, Taiwan, and also Mexico. Affluence is larger than technology, so the positive dots are on the left: China, India, Russia, Brazil, rest of the world, and several East European countries. All of you. Mexico is. Well, and in between there are some countries that have a net effect of 0. The technology effect is in general negative. The affluence effect is in general positive. But also observe that the domestic effect is typically much greater than the foreign. So because the effect works mathematically in a direct way and there are no second higher order. Yeah. Again, the lower income countries are on the left, the richer countries, the high income countries are on the right. So there's a clear difference in stages of development. Well, this is basically repeating. So let me. Yeah, this is what I mentioned also Monday. That was based on this paper. That if you look at the difference in the decrease in the footprints, I said that was a turning point. Perhaps yes, it's good news. In particular, in Europe, the carbon footprint decreased by 0.6 gigatons. Congratulations! But if you read the report by from the Paris conference, then to arrive at decreased temperature rise between 1.5 and 2 centigrades, the global decrease required should have been 1 to 2 gigatons in this period in the 2020s. And that is 2 to 5 times as much as we do now. So yes, there is good news, but it's not good enough. Well, the same thing for relatively poorer countries, middle-income countries. They still are in the process of building up their infrastructure. That will all vanish. At a certain stage, the infrastructure is there, and you start consuming more, which is relatively clean. So then the footprint will start to decrease. Good news, yes, good news in principle, but you should realize that half of the world population lives even in low and lower middle income countries. So they have still to go through this process. Do you want to see this? It's the last set of slides. It's 1 o'clock. I'll do say I've had enough. 9 hours of all this. You tell me. But this is about energy transition. It's probably been applied to energy. And so the starting point is renewable energy. The use of renewable energy changed over time, and how come? And again, that leads to a structural decomposition analysis. And with all the structural decomposition analysis, you see that, in particular in an environmental area, it's always we eat more, there's more people, and several other usually smaller drivers. And of course, the technology affect more efficient renewable energy. So using the standard structural decomposition analysis, we can do that. But not here. In this paper, we split renewable energy use into total energy use, and that is used more energy efficient, and energy transition. So there's one thing that using your electricity, for example, in machines more efficiently, running your machines on less electricity, that is one thing. And the other thing is that your electricity is now, this year, made with solar panels or wind energy in comparison to fossil fuels previously. And why is this important? In the standard answer, you would say standard approach, more consumption, more people will increase the use of renewable energy use, and the more efficient use decreases the total. In this paper is something similar. But there we say more consumption, more people increases total renewable energy use. More efficient energy use as a decreasing effect. But energy transition, if all of a sudden we start transiting to solar and wind energy, that will increase the renewable energy use. Now, why do we think that this is important? Take a very simple example. Take the example where we've done the calculations and more consumption per person is good for 75% of increase in renewable energy. More people, 30%, more efficient use of renewable energy, minus 10%, and the rest, 5%. Now, you would say that in terms of efficient renewable energy use, there's not much going on in this case. But it can be the case that this reflects a situation where you have done an excellent, super job in terms of energy transition. It could be the case that this more efficient renewable energy use is due to using less electricity on your machines, which help enormously. So all your production is done more efficiently in terms of energy. Plus, you have changed a whole lot of energy from dirty energy production to renewable solar. And so this indicates this minus 10% hides an excellent job. Or you could have been doing a terrible job, where basically you got less efficient and still you went back from, you threw away all the solar panels, all the wind energy, and go back to power-based electricity. And from this number, I cannot tell, this minus 10%, I do not know whether you have done an excellent job or a lousy job. So therefore, that's the reason why we say this structural decomposition analysis, of course, can be done, but doesn't answer this question. So we combine the drivers very much in what we have seen so far. So the technological changes is in energy per dollar, so energy intensities, but it also includes the changes in the input coefficient, in the technical input coefficients. You have the changes in the trade structure, as we saw in the previous hour, changes in the consumption bundle, final use. So that is per capita affluence. We have changes in population, and now we have the changes also in energy transition. So it is measured at the share of renewable energy, 20%, and in the total use of energy. If that percentage increases, the share of renewable energy increases. We use the wire database. Well, we use the wire database and the energy data that were developed by Victoras himself. These are the sources. Who was interested in, if you were the one working on your constant prices, check this paper. Because there are, so first of all, these are the outcomes. I'm going through the outcomes. And for example, this is the outcome for affluence. This is the outcome, as I will tell you, next is the outcome for efficiency. And if you run the calculations with tables in current prices, then these go, because this part due to inflation is overestimated in current tables, and this part in tables in current prices is. And the results are in the paper. You see what the effect. And much of what happens in between remains more or less the same, because these are based on coefficients that are of the type dollar per dollar. Then it doesn't matter too much. So the total increase was 22 exajoule. Sorry. Affluence in purple increased by 32 exajoule, and population 11 exajoule. So consumption together 43 exajoule, and that is 2 times as large as the actual increase in renewable energy use. And these are the numbers that we saw also in the previous presentations, and this is also the number that people often find. Technology, again, a reduction in energy intensities led to a decrease in energy use. The dark blue, that is the effect of energy transition, and that is very little. Yellow, the trade effect, we said in this time frame it has a larger effect that is not found for energy. So, yeah, here we go now to the separate countries. That is interesting because there you see a different pattern. So we have blue as population, dark blue, light blue is affluence, final demand per capita. White is trade structure. Technology is, what is this? Orangey, and red is transition. And observe, the dots give you the territorial renewable energy use. It's 8.9 for the rest of the world. And this is 9.3. The production per capita. Technology is minus 6.5. So that is how the bars should be interpreted. And the red bars give the transition. We saw that for the transition, the global effect was very modest. But if you look at the red bars at the country level, you see that in India, and in China, and the rest of the world, it's negative. Well, you see that a substantial positive part, indicating a positive amount of transition, an effect of transition in Europe, in the US, and East Asian countries. So there is transition is taking place, but not at a global level, because in India and China, transition is not taking place, or the effect is measured as negative. Observe also that the trade structure effects are positive for China and the rest of the world. Of course, they are, and that is because the producers and consumers move away from Europe and US inputs, and they now move to Chinese and rest of the world inputs. And the inputs from China and rest of the world are produced in a slightly more dirty way than in the old-fashioned Europe and US inputs. That effect you see reflected here in the white little bars. So energy transition, small but positive effect on the global renewable energy use, positive effect for Europe, US, and East Asia, negative for China and India. And same mentioned already. Trade structure and the usual suspects, affluent and technology. I should mention, by the way, the negative effect for energy transition in China does not mean that they've gone back to fossil fuel energy use. It's just that the extra use of fossil fuels is larger than the increase in renewable energy. That is still an increase in renewable energy, but the use of non-renewables is a bit larger, and therefore the ratio decreases, but it's not the case that they throw away their wind turbines. Okay, thank you. Thank you for your attention, not only today, but this week. Must have been a terrible week for you. Hard work. Hope to see you again.
We want to say thank you to the Professor Witzenbacher. It's an honor for us to give him at the Institute, and that he accepted to take this, well, to make this course and all the discussions in the different programs that he has been. So we really appreciate here, Professor, and say thank you to you too, because you put your time and your effort to be in this course, and I appreciate a lot your presence. And we are going to move to do many things as this we expect in the future for the Institute. So you are invited to these all things. And thank you very much. And thank you, Professor. It's an honor.